Hello everyone. In a previous video lecture, we have seen the concept of Gauss law and divergence theorem. In a today's video lecture, we will discuss about the concept of electric work and potential. Okay. So first we will study the work done for moving a point charge from one point to another point in the presence of electric field. Okay. So if we move a charge in an opposite direction to that of electric field or E bar, then an external work is required. So while moving a charge, then energy is expanded and this is called as potential energy. Okay. So let us see first case, work done in moving a point charge. So if an electric field E bar and a charge Q experiences a force that is F bar, then suppose we have to maintain this charge Q in the equilibrium condition, then an equal but opposite forces should be applied to this point charge, that is Q. Okay, and as we know that the force experienced by the charge Q is nothing but force F is equal to Q into E bar. Okay, or we can say electric field intensity is equal to force per unit charge. Okay, so in this equation we have to just multiply this E bar with this Q, then we'll get the value of F, that is force is equal to Q into E bar. So the force is applied to the charge Q in order to maintain it in the equilibrium is Fa is equal to, this is Fa is equal to minus of Q into E bar. Okay, so in this case we are moving the charge against the electric field, that's why negative sign is there. So that means we are applying a force equal and opposite to that exerted by the field, and this requires us to expand the energy. So we are doing work to move the charge against that electric field. So the work is defined as force acting over a distance, that means W is equal to force into displacement. Okay, so suppose now we have to move the charge in the direction of electric field, then in this case we do not have an expand the energy, that means we are not doing the work, rather the field does the work. And if we are doing the work while moving a charge against electric field, then we are applying the force, that is Fa, to cause differential displacement, that is dl. Okay, so then differential amount of work, that is dw, is given by this equation. Dw is equal to Fa into dl, that is dw is equal to force into displacement, that is dl. Force into displacement is equal to dw. Okay, so here this F is nothing but force applied to the charge against electric field, that is E bar, then dl is the differential displacement of the charge, and al is nothing but the unit vector in the direction of this dl bar. Okay, so we'll get here dw is equal to force into displacement formula, and we know that F is nothing but it is equal to Q into E bar having negative sign. So that's why we can put here the value of F is equal to minus of Q E bar into dl is as it is. So thus the total work required to move the charge from the finite distance is given by this formula, that is W is equal to initial to final displacement inside integration dw. Okay, so here we have to put this value of dw, that is minus of QE bar into dl bar in this equation. So we'll get W is equal to integration limits from initial to final inside integration, value of dw is minus QE bar into dl bar. So we'll get W is equal to outside integration minus of Q, then inside integration initial to final limits E bar into dl bar. Okay, so this is the total work done which is required to move this charge a finite distance from the initial position to the final position. Okay, so while moving the charge we can choose different paths, but remember that work done is always independent of the path. This is very important point, that is the work done is independent of the path. Okay, so there are some observation about this work done. If you observe this equation, then we can say that the work done in moving a point charge from that one position to another position in the presence of electric field, it is independent of the path followed. That means if the selected path is perpendicular to E bar, then the work done is 0. That is W is equal to minus Q integration of initial to final inside integration E bar into dl bar. This is our work done equation. And here if we select the perpendicular path to that E bar, that means what? The angle between E bar and dl bar is 90 degree. Why? Because they are perpendicular, and we know that if the two axes are perpendicular to each other, then the angle between them is 90 degree. Okay, so here we will consider the E bar and dl bar both are perpendicular to each other, so that's why the angle between them is 90 degree. So according to the definition of dot product, we can say A bar dot B bar is equal to AB cos theta. Okay, we have to take here dot product of this E bar into dl bar is equal to mod E bar into mod dl bar cos theta. The value of theta is 90 degree. We know that cos 90 is 0, so that's why we'll get value of E bar dot dl bar is equal to 0. So thus in this case work done is 0. So here if the motion of charge Q is against that electric field, then external force is required, and in this case work done is positive. When work done is positive? When the motion of charge Q is against electric field, then we have to apply here external force. In this case the work done is positive. And if the motion of charge Q in the same direction as that of applied field, then external force is not required, so that's why in this case work done is negative. Okay, if Q and field are same, are in the direction of if Q is in the same direction of applied field, then we can say external force is not required, so that's why work done is negative. And if the motion of charge Q is against the electric field, then external force is required, so that's why in this case work done is positive. Okay, so while calculating the work done, if selected path is closed loop like this, it is closed loop, that means starting and ending points are same, so in this case the work done is. Next point is potential. We have studied that the electric charge Q which will produces the electric field intensity, that is nothing but what? E bar. And consider now that we are placing another test charge, that is Q0, then the force F is exerted on that charge Q0. Okay, so the ratio of force to the test charge Q0 is called as the electric field intensity. That is nothing but what? E is equal to F upon Q0. Okay, so after that let us consider the electric field intensity is in the plus x direction. This is x axis and electric field intensity is in the direction of x bar. Okay, so then if we have to move the charge in the opposite direction to that of x bar, then work is required to do it. So this situation we can see in this figure. So now in this case what happened? Work divided by charge is equal to force into displacement upon charge. Means what here? We know that W is nothing but what? That is work done, which is equal to force into displacement. Okay, so here we can write W is equal to force into displacement, then upon charge is as it is. Okay, so here for a small work done we use notation dW and the corresponding force is dF and the displacement is dx. Okay, so in that case what happened, we can write instead of full W or charge, we can write here dW upon Q0 is equal to small differential force, that is dF, and small differential distance or displacement, that is dx. Okay, so again we know that electric field intensity is nothing but what, F divided by Q. So we can write here F is equal to E into Q0. So that's why this dF becomes what, dE into Q0. Okay, so we have to put this value dF is equal to dE into Q0 in equation number 3.3.2. Then we'll get dW upon Q0, that is left hand side is as it is equal to dE into Q0 into dx upon Q0. Then what happened, this numerator Q0 and denominator Q0 get cancelled, and the remaining term is dE into dx, and left hand side, that is dW upon Q0 is as it is. Okay, so here in this case what is mean by this dW, that is work done is moving a charge, then Q0 it is a test charge, then dE is the magnitude of differential electric field intensity, dx is nothing but distance moved by Q0. Okay, then after that if you want to calculate the unit of this potential or this equation, then we can write dW upon Q0. We know that the unit of W is nothing but joule and the unit of Q0 is nothing but Coulomb. So we can write joule upon Coulomb is equal to the unit of dE, that is differential electric field intensity, that is volt per meter. So we can write dE is equal to volt per meter into dx is having unit only meter. Okay, so here again this meter get cancelled, then joule per coulomb is equal to volts. That means what, the dimension of work per charge are nothing but the potential, that is volt. Okay, so the difference in potential dV across the distance dx is defined as the work or energy per unit charge required to Q0 for the distance dx. Okay, next point is the potential difference between 2 points. This is the case where we have calculated the potential due to single point charge. Next we have to calculate potential difference between the 2 points. Then in this case the potential of point A with respect to point B is defined as the work done is moving a unit positive charge from B to A. That means what, here we have to calculate the potential difference between point A to B. This is point A and this is point B. Then the work done is moving up this point charge from B to A. Okay, so we can write the potential difference between point A and B is denoted by VAB, that is VAB is equal to W upon Q, work per unit charge. Okay, so this is the potential value, that is W by charge. Okay, but here we have to calculate the potential difference between point A to B, so that's why we can write here V of AB is equal to W of W divided by Q. Okay, now to move this positive charge from B to A, then some external source is required. So the work done by that external source in moving a charge Q from the one point to the another point, the electric field is given by W is equal to minus of Q integration starting limit initial to final inside integration E bar into dl bar. This is the equation of work done we have already seen. Then in this case the initial point is called as reference point. Okay, so here we can write W is equal to minus Q is as it is, the initial point is B, to A inside integration E bar into dl bar is as it is. So here note that the negative sign is appear. Means what? This is the force which is related to E bar. So that's why we have to take here F is equal to minus of Q E bar. Okay, so due to that external force we have to take here this minus sign. Okay, then we'll get here W is equal to minus of Q integration of starting limit B to A E bar into dl bar. So we can write here V is equal to W upon Q. So if we shift this Q to the left hand side, then it will give W by Q is equal to this right hand side is as it is. And as we know that W by Q is nothing but V, that is nothing but potential. So we can write V of AB is equal to integration of this integration minus B to plus A E bar into dl bar. Okay, so here the unit of this potential difference is volt, or we can say joule per coulomb. Okay, in next point we have to study the potential of a point charge. So for this, let us consider the point charge, that is this is a point charge, small charge, that is plus Q, which is placed at the origin of this spherical coordinate system. This is the spherical coordinate system. Okay, and this point charge is placed at this origin. So the electric field at this point Q is in the radial direction. Okay, so we can see these are the radial directions. So now consider 2 points A and B. Let us consider this is point A and this is point B, which is placed in this system. Then what happened? The point A is at the radial distance RA and the point B is at the radial distance RB from this origin. Okay, so here we know that the generalized formula for the electric field intensity due to point charge, that is equal to E bar is equal to Q upon 4 pi epsilon 0 R square into AR bar. This is the generalized equation for electric field intensity due to point charge. Okay, then after that what happened? The potential difference between point A and B can be calculated, which is equal to VAB is equal to minus of integration RB to RA E bar into dl bar. Okay, so next if you want to define this dl bar, that is differential length, then we can write in a spherical coordinate system as dl bar is equal to dr AR bar plus r d theta a theta cap plus r sin theta d phi a phi cap. Okay, this is the differential length element in case of spherical coordinate system. Okay, now after that we have to put here the value of E bar, that is Q upon 4 pi epsilon 0 R square into AR bar, and dl bar is also given. So we have to put all these equation in this equation number 3.3.10, that is V of AB is equal to minus of integration RB to RA as it is, value of E bar is Q upon 4 pi epsilon 0 R square into AR bar into dl bar is as it is. Okay, then in next step what happened? If we take here the dot product of two different unit vector, that is r bar into theta bar or theta bar into a phi bar, then it will gives answer as a 0. Okay, but if we take here the dot product of same unit vector, then it is considered as a 1. Okay, so we can write here AR bar dot AR bar is equal to 1. So that's why VAB is equal to integration of RB to RA Q upon 4 pi epsilon 0 R square dr is equal to minus of Q upon 4 pi epsilon 0 integration of RB to RA inside integration 1 upon R square into dr. Okay, so here the integration of 1 upon R square is minus 1 upon R and the limits are from RB to RA. Then it is given by V of AB is equal to q upon 4 pi epsilon 0 into, we have to put here upper limit minus lower limit, that is 1 upon Ra minus 1 upon Rb. So we'll get V of AB, that is potential difference between point A and B, is V of AB is equal to q upon 4 pi epsilon 0 Ra minus q upon 4 pi epsilon 0 Rb. Okay, so this is the final equation of potential difference between point A and B. So today we will stop here with motivational quote. Today's motivational quote for you is, never stop doing your best just because someone doesn't give you credit. So friends, if you really like my videos, then please like, share and subscribe to my channel. Thank you for watching my videos. Thank you so much.